Okay. Let us now start solving the exercises at the end of section 4.4. Once we finish this, we will then be, our entire study of rational numbers will be over, the initial study. We can then go to the construction of the real number system. So, in the first one, we have been asked to prove proposition 441, the proposition which asserts the existence and uniqueness of the integer part of a rational number. Just to recall the statement, if we are given a rational number x, then the proposition states that there exists a unique integer n such that n is less than or equal to x and x is strictly less than n plus 1. This integer n be called the integer part of the rational number x. Now we are going to prove the existence and uniqueness of n. So there will be two parts to this solution. The case x equal to 0 is obvious. So we assume x to not be 0. Why is the case x equal to 0 obvious? It's because, but before I write this, I should mention what I am doing here. We first prove that there exists an integer n such that n is less than or equal to x and x is less than n plus 1. So in the first part, we are proving existence of n, and then we will prove uniqueness of n. Okay, now here the case x equal to 0 is obvious. In this case, you can take, I should not write u. We can take n equal to 0. So when x is 0, n can be chosen to be 0 because 0 is less than or equal to 0, which is strictly less than 0 plus 1. So we assume x to be non-zero. First we consider the case where x is positive. Then, since x is a positive rational number, so by positivity of x, by the definition of positivity, there will be two positive integers p and q for which x is equal to p divided by q. Then x is equal to p divided by q for some positive integers p and q. Okay, now we are going to use proposition 239, which is the division algorithm in the system of natural numbers. These are positive integers, so they in particular are also natural numbers, in fact positive natural numbers. So we can use proposition 239. Now by proposition 239, there exist natural numbers, say T and R, such that P is equal to TQ plus R and R is non-negative and less than Q. Okay. Then what about TQ? Note that TQ is less than or equal to TQ plus R. Why is that so? Because R is non-negative. To both sides of this inequality, you can add TQ. That will give us this inequality. And this is equal to P, but TQ plus R at the same time is less than TQ plus Q. Why? Because now you use the second inequality. To both sides of the second inequality, you add TQ. That will give you this last inequality. So this is equal to T plus 1 times Q. Dividing throughout by the positive rational number Q, we get Q is an integer, but that is why it's also a rational number and it is positive. So we can divide by Q and the inequalities will not get reversed. So we will get this. First, if you divide this one by Q, then you get T less than or equal to TQ divided by Q means P divided by Q. So that is equal to X, and that is less than this divided by Q is T plus 1. So we have actually found an integer T, which in this case turns out to be a natural number, that is a non-negative integer, such that these inequalities are true. In other words, in place of n now we have T, but this is when X is greater than 0. Next, let X be less than 0, then minus X is greater than 0, and so by what we have proved above, there exists an integer m such that m is less than or equal to minus x, which is less than m plus 1. This implies if you now multiply throughout by minus 1, you will get these inequalities. Minus m minus 1 is strictly less than x, and x is less than or equal to minus m. If x is equal to minus m, since x is less than or equal to minus m, so there are two cases, either x is equal to minus m or x is strictly less than minus m. If x is equal to minus m, then minus m minus 1 is less than or equal, oh no, what I am writing is not correct. Then minus, I think I need some ink. Minus m is less than or equal to x, which is strictly less than minus m plus 1. This is one case, and if x is strictly less than minus m, minus m is less than or equal to x, which is less than minus m plus 1. I hope it's visible. For some reason the ink is not coming properly. X, so this is minus m plus 1, and if x is strictly less than minus m, then minus m minus 1 is less than or equal to x, which is less than minus m. So note that in any case we always have an integer. In this case, when x is minus m, then we can choose our integer n to be minus m itself, because minus m is less than or equal to itself, and it is strictly less than minus m plus 1. And in the case where x is strictly less than minus m, then in place of n we can choose minus m minus 1. Okay, and since we already have these inequalities, this strict inequality where minus m minus 1 is less than x also implies the non-strict inequality. The converse is not true. Okay, this less than or equal to x does not imply this strictly less than x, but the direct implication is true. If the strict inequality is true, then this is also true, and x in this case is strictly less than minus m. So in this case also we have got an integer n for which these inequalities are true, and in our case now n is minus m minus 1. Hence we have proved that for any rational x, there exists an integer n for which those inequalities are true. For which n is less than or equal to x and x is strictly less than n plus 1. We now turn toward uniqueness of n. Now we want to show that this integer n that comes from a because of x, it is unique. It is uniquely determined by x. Suppose there exist two distinct integers m1 and m2 such that m1 satisfies these inequalities and m2 also satisfies these inequalities. So we have supposed that no, such an n is not unique. We now want to derive a contradiction. So because we have supposed m1 and m2 to be distinct, so one of them will be less than the other. We assume without losing generality that m1 is less than m2. Okay, now two cases arise. If m1 is non-negative, then what happens? Then we can write like this. Oh, but before we consider these cases, I think there is one more step. Have I written it here? No. Okay, let us proceed and see what we get. If this is the case, then m1 is strictly less than m2. Okay, m2 is less than or equal to x, and x is again strictly less than m1 plus 1. The first inequality is the one we have assumed. The second one is coming from here, this one, and the third one is coming from here. Okay, so we have a sequence of three inequalities. Now, by proposition 2 to 12e. Proposition 2 to 12e is the one where we have properties of order for natural numbers. In order to be able to apply that proposition, we need all these integers to be natural numbers. That's why we need this condition, m1 greater than or equal to 0. And because of this condition, m1, m2, x, not x by the way, x is a rational number, m1, m2, m1 plus 1, these are all natural numbers. And what was part E? In part E we had this: if a and b are two natural numbers, then a is strictly less than b if and only if the successor of a is less than or equal to b. For us now the successor is a plus 1. Okay, so we are now going to apply this in this to this situation, to these inequalities. So then by proposition 2 to 12e, we have m1 is strictly less than m2, so the successor of m1 will be less than or equal to m2. The successor of m1 is m1 plus 1. So this is less than or equal to m2, which in turn is less than or equal to x, and this is less than m1 plus 1. Note carefully that this inequality is strict. That is, we have m1 plus 1 strictly less than m1 plus 1, which is a contradiction. It contradicts trichotomy of order relation. Which is a contradiction. Okay, now we look at the other case when m1 is negative. Then again we are going to take the help of these inequalities, but now we are going to create positive integers from this negative m1. That is, these inequalities means these inequalities. Minus m1 minus 1. So here we are multiplying throughout by minus 1. So minus m1 minus 1 is strictly less than minus x, that is less than or equal to minus m2, which in turn is less than or equal to, okay, what am I writing? This one, the negative of this is strictly less than the negative of x, which is less than or equal to the negative of m2, and m2 is strictly less than the negative of m1, and so by same result, proposition 2 to 12e again minus m1, which is the successor of minus m1 minus 1. This is the successor of that number, and note that these integers minus m1 minus 1 minus m2 minus m1, these are now all natural numbers, so we are able to use the proposition. So this is strictly less than minus x, which is less than or equal to minus m2 and m2 is strictly less than minus m1, that is minus m1 is strictly less than minus m1. Again a contradiction. So our supposition is wrong. That is, for a given x we cannot have two such integers. Since we have already proved that there is at least one such n, so it now is unique. This proves that n is unique, and this completes the proof of the proposition and hence the solution to this exercise. The next exercise 4.4.2. This exercise starts with a definition. A sequence A0, A1, A2 and so on of numbers, and the numbers can either be natural numbers, integers, rationals, or reals, that is real numbers. Although we haven't constructed the real numbers yet, but in the next chapter we are going to construct them. So there also this definition will work, and the definition is this: such a sequence is said to be in infinite descent is in infinite descent, that is, its terms are decreasing. The further you go down the sequence, the smaller the terms get, and there is no end to it. Infinitely it's descending, the values are descending. If we have an strictly greater than the next term an plus 1 for all natural numbers n, that is, all natural numbers n's means not that the suffixes are natural numbers. The numbers themselves can be either natural numbers or integers or rationals or reals, but the suffixes, the labels, are natural numbers. That is, A0 is greater than A1, A1 is greater than A2 and so on. Okay, so this is the definition of a sequence in infinite descent. Now comes the exercise. There are two parts. In part A we have to prove this. Prove the principle of infinite descent. And the principle is simply this, that it is not possible to have a sequence of natural numbers in infinite descent, which is in infinite descent. Same thing. And elaborate hint is also given. Assume for sake of contradiction that you can find a sequence of natural numbers which is in infinite descent. Okay, so which is nothing but the existence of such a sequence is the negation of what is being stated as the principle of infinite descent, that there is at least one sequence of natural numbers which is in infinite descent, and then we will have to derive a contradiction, and specifically like this: since all the ANs are natural numbers, you know that AN is non-negative for all n. Yes, this we already know. Now use induction. Okay, some of these hints are almost an entire solution. Then use induction to show in fact that AN is at least k for all n for all natural number labels and all k also, where k is a natural number. And obtain a contradiction. Okay, so this is part A. We have to prove here that the system of natural numbers has no sequence which is in infinite descent, and this is the strategy of the proof. and in part B we look at other sequences. Does the principle of infinite descent work? If the sequence is allowed to take integer values. Instead of natural numbers. In that case also, that is, if we consider a sequence where the terms are integers, then can we have a sequence which is in infinite descent? And what about the rationals? What about if it is allowed to take positive rational number values? Okay, I think I will barely have space to write this. Instead of natural numbers, you can understand I am not writing that. Explain. Okay, so let us now look at the solution. The proof that we have come across in the text of the fact that there is no rational number whose square is equal to 2 depends on this one. Okay, depends on the principle of infinite descent. So here we exactly follow the route that has been laid out by Tau. An. Suppose the sequence of natural numbers is in infinite descent. We now show by induction that An is greater than or equal to k for all n and k, both of which are natural numbers. We know that since all the ai's are natural numbers, so An is greater than or equal to 0 for all n. So this is the basis for our induction, which we just simply have from the properties of order relation on the system of natural numbers. Now we are going to make the induction hypothesis. Assume that an is at least k for all n belonging to the system of natural numbers where k is some natural number. Now our aim is to simply show this, that an is also greater than or equal to k plus 1 for all n. Suppose this is not true, that means there is at least one value of n for which the corresponding an is strictly less than k plus 1. It's not greater than or equal to k plus 1. So that is the supposition we are going to make. So it's a combination of induction and the method of contradiction. Suppose an naught, say, is strictly less than k plus 1 for some natural number n naught. But what is the induction hypothesis? The induction hypothesis says that an is greater than or equal to k for every n naught. For every natural number n. So in particular for this natural number n naught also, an naught will be greater than or equal to k. Now by the induction hypothesis, k is less than or equal to an naught. So we have k less than or equal to an naught, and this is strictly less than k plus 1. Now you look at these inequalities. An naught is a natural number that is greater than or equal to k and less than k plus 1. If k is not equal to an naught, say if that happens, then k is strictly less than an naught, which is again strictly less than k plus 1. And here instead of thinking extremely logically about these things, you just simply think of the situation. You have a natural number k and you have k plus 1. Can there really be a natural number an naught between k and k plus 1? No, but we need a proof for concluding that this is not possible, and this leads to a contradiction, just like in the previous solution. or if you want you can use that proposition to 12e again here. So here the contradiction will be obtained by imposing that proposition to this inequality. This will tell us that the successor of k, which is k plus 1, will be less than or equal to a n naught. Okay, and since a n naught is strictly less than k plus 1, you will encounter the contradiction that k plus 1 is strictly less than k plus 1. You have to of course look at all the cases. Here however k is not negative, so that thing at least is not there, but you can understand. The thing is that you can carry out an argument that we already have come across in the previous solution. So we are just simply going to mention that one such argument can be applied here to get a contradiction where we used proposition 2 to 12e. So we must have, so that means this is not possible. K cannot be different from a n naught, it has to be equal to a n naught. K is equal to a n naught. But then if k is a n naught, what sort of, what else can we say from this new situation? But then this contradiction, this new contradiction arises. K is equal to a n naught, keeping in mind that our original sequence a n is in infinite descent, so the next term a n naught plus 1 will be strictly less than a n naught. Okay, but again the induction hypothesis is already there. A n is greater than or equal to k for every n. In particular for this value of n naught plus 1, also this will be greater than or equal to k. That is, k is strictly greater than k, which is not possible. So again we have come to a conclusion which is not possible. So why are these wrong things arising? They are arising from our supposition that a n naught is less than k plus 1, which is thus false. It cannot be true. So our supposition, let us write the supposition a n naught strictly less than k plus 1 is false. In fact, that is not actually the supposition. The supposition is the statement that there is a natural number n naught for which this is true. So that means no such natural number can exist. That is, we must have a n greater than or equal to k plus 1 for all natural numbers n. This completes the induction. So this completes the induction. What have we now proved? We have proved that every natural number is greater than or equal to every other natural number. In fact, greater than or equal to itself also. And this will contradict a result which we have already proved before. Thus, an is greater than or equal to k for all n and k belonging to the set of natural numbers. This contradicts was it proposition or lemma? Proposition. Proposition 441. Okay, it contradicts proposition 441. In fact, in proposition 441, what we had is that the one we have proved just now. If you have a rational number x, then it has an integer part m. In fact, the integer part is unique. And this proposition in particular tells us that for every rational number, you can find an integer n such that n plus 1 is greater than x. In particular, in place of n, you can take a positive integer. So, a consequence of this inequalities is that for every rational number x, there exists a positive integer n that is strictly greater than x. Since natural numbers are also in particular rational numbers, so for them also for any one such natural number, you can find a positive natural number or a positive integer that will be strictly greater than that natural number. Here, however, we see that whatever natural number we are taking, an, okay, an turns out to be greater than or equal to every natural number. So that directly contradicts this second part of proposition 441. So that's why we are writing this contradicts proposition 441. So our initial assumption is, initial supposition is false. So our initial supposition is false. That is, no sequence of natural numbers can be in infinite descent, and this is precisely the principle of infinite descent, which we have now proved. Okay, now we come to part B. In part B, we have been asked that if we replace the sequence of natural numbers by sequences of integers or by sequences of positive rational numbers, in that case is the principle of infinite descent true. Here, in none of the other cases, the principle of infinite descent is true. Infinite descent is not true for sequences of integers and for sequences of positive rational numbers. The sequences -1, -2, -3 and so on, and one comma 1/2, 1/3, etc. demonstrate this fact. This is a sequence of integers where you can clearly see that each term is strictly less than the previous term. So this sequence is in infinite descent. So we can have a sequence of integers that is in infinite descent. Now if you think that this is happening because we have taken negative integers, and so there is no bound in no bound to the size of the integer that we can take, that is, we can make the integers as small as we want in terms of order. However, even if you restrict the left hand side of your number system by taking only, say, positive integers, there also you can create a sequence in infinite descent like this, where again each term, all of these are positive, I said positive integers, positive rational numbers, all of these are positive rational numbers, and each one is strictly less than the previous one. So this is in infinite descent. So that's why the principle of infinite descent fails to be true in the other systems. And finally, there is this third exercise where we answered you recall there were some gaps in the proof of proposition 444 where we used this y. Some gaps were marked with y's. So we now have to answer these y's in this next exercise. Fill in the gaps marked y. Okay, now we have to recall what were the things, what the things were in the proof of proposition 444. Recall that we defined what we mean by even and odd integers. Okay, and we also said that every integer is either an even integer or an odd integer. I don't think we did this in general for integers, but rather we did this for in proposition. Yeah, we needed this only for positive integers. Anyway, whatever it is, we now have to show that any integer is either even or odd and never both at the same time. So that was the first one. And here we are going to take the help of proposition 239, that is the division algorithm available in the system of natural numbers. There exists unique integers t and r. I should not write unique integers, unique natural numbers, or instead of writing natural numbers I can simply write this symbol, that unique natural numbers t and r such that p is equal to 2t plus r, where r is non-negative and r is less than 2. This p is the p that we have in the proof of this proposition. Okay. So because r has only two possibilities, one of them is 0 and the other is 1, so let us see what happens in each case. So we have only two possibilities. If r is equal to 0, then p is equal to 2t and hence p is even. And the second one is this: if r is equal to 1, then p is equal to 2t plus 1 and hence p is odd. So we see that the integer p can either be even or odd, but can it be both at the same time? It cannot be both at the same time, and that follows from uniqueness of r. R cannot be both 0 and 1. It is unique. For a given p there is only one r, and in this case, by the way, if you look carefully, we are dividing p by 2. Where is it? Here. So here the divisor is 2, t is the quotient and r is the remainder. P can't be both even and odd because r is unique. Okay, so uniqueness of r prevents an integer to be both even and odd at the same time. Okay, now what was the next y? In the next y, it has been said that the square of an odd integer is an odd integer. If p is odd, then p is equal to 2k plus 1 for some k belonging to n. Then p square is 2k plus 1 whole squared, that turns out to be equal to 4k square plus 4k plus 1, and that becomes 2 times 2k square plus 2k plus 1. This is again a natural number, and so p square is odd. And in the final y, in the third y, we have been asked to show that from the equation p square equal to 2q square, one can conclude that p is greater than q. That's what we have to show. Okay, so from p square equal to 2q square, we have p plus q times p minus q equal to p square minus q square, but p square is 2q square, so p square minus q square will be equal to q square, and this is strictly greater than 0. Excuse me. So this is strictly greater than 0. And why is this strictly greater than 0? The last inequality follows from the fact that q itself is greater than 0. In fact, it just needs non-zeroness of q. That makes the square of q positive. Otherwise, if when q is 0, then the square is also equal to 0. Since p plus q is positive, and for that C proposition 2 to 8, the sum of a positive natural number and another natural number is positive. That is the statement of proposition 2 to 8. So that's why by lemma 4.1.11 C, p minus q must be positive. The product of these two integers is positive, and one of them is positive, so the other also has to be positive. So from there we are concluding that p minus q should be greater than 0, or p has to be greater than q. So this is what we wanted to show. So these are the answers to the 3 whys. This completes the third exercise, and it in fact completes this set of exercises. We have thus completed chapter 4 entirely with all the exercises now solved for us. In the next video, we shall start constructing the system of real numbers. And there, as we have already said, we will take the approach of defining real numbers as some sorts of limits of Cauchy sequences of rational numbers. We will see what those things mean. Okay, so I end the video here. If you are new here, please subscribe to my channel, A Mathematical Room. So this is me, Lucifer, signing off for tonight. Have a nice night.